Hello, welcome back. This is Professor Robert Needing, and I'll be teaching section 6.4, the distribution in the difference of means. First thing that we'll want to make sure that we have in front of us when we're working all the time is our formula sheet. We'll be working today with the difference of mean confidence interval level and the test statistic for the difference of means. Remember, since we're working in a mean, it's a t-distribution, not a z-distribution. It's slightly different. Calculator commands are slightly different, but overall it does the same thing, but works within the population of a mean instead. So the standard error for x bar 1 minus x bar 2, or the difference in two means, is the formula that we have. Now, the problem is that sigma, referring to the standard deviation of the population, is something that we don't actually have to work with. So we're going to work how to get through that and how to deal with those particular items. So let's start by simply just revisiting the central Lierman theorem. Remember that we can distribute something normally on the approximation that we have both a sample size or at least 30. So what we need is we need both, and we're going to make sure we highlight this, both of our sample sizes, so it's going to be N1 and N2 simultaneously, are going to have to be at least 30. That's one piece of criteria that we can use on a normal distribution. Now, remember that in a normal distribution, for instance, n0, 1, we distribute on a center piece. This is where the center of our distribution will take place. And this is our standard error, if you will, for our calculation. Our standard error formula, as you can see, uses the standard deviation squared divided by the sum of n, or the population of n. Now, it goes on to tell us, and like I stated kind of earlier, is that we don't know the population standard deviations. So we're going to estimate them, and what we're going to use to estimate them with is the standard deviations from the sample sets. The standard deviations of the population will be replaced with the standard deviation of the samples. And I'll show you how to get those standard deviations using your statistical tools in both StatKey and in your calculator. So on a t-distribution, when we replaced sigma 1 and sigma 2 with standard deviation 1 and standard deviation 2, we change it from a standardized test statistic, or a z-value, into a t-distribution. That's one of the criteria we have for if we're in a t-distribution. It says, if the population is approximately normal, or, and that's going to be a big word for us, or if the sample sizes are large enough. So we have two criteria. One, is it approximately normal, meaning does it make a smooth curve? Or do I have greater values of 30? So if I can meet one of these criteria, I will be able to institute this t-distribution. It says under H sub O that the standardized test statistic for a difference in means follows a t-distribution with degrees of freedom. Remember, the degrees of freedom are always one smaller than the set, but now we have two sets. So now we're going to focus on the smaller of either N1 or N2. And our distribution will take place according to the formula. We'll walk through the formula, and we'll make sure that you can utilize all aspects of the formula. So here goes a question for us to look at. A t-distribution is an appropriate model for a distribution of the standardized differences in two sample means if both of the sample sizes are large enough, but the distributions are not normal. So large enough meaning they're greater than 30, but it tells us clearly that they are not normal, meaning they could be skewed. Well, remember the criteria on the first slide was if both sets are greater than 30, then we can use the t-distribution. This would be a true statement. Second question. A t-distribution is an appropriate model for a distribution of the standardized differences of two sample means if both of the sample sizes are small, but the distributions are normal. Remember, this was a two-sided coin here. Either I could have large enough sample sizes, greater than 30, or they could tell me that they were normal. Again, true. A t-distribution is an appropriate model for a distribution of the standardized difference in two sample means if one of the samples is small and one is large, but the distributions are not normal. If the distributions are not normal, both sets must be large, If both sets are not large, then it is not an appropriate model for distribution. We have a question that says, samples of size 45 from population 1 with a mean of 3.4 and a standard deviation of 1.5, and samples of 45 from population 2 with a mean of 2.8 and a standard deviation of 1.1. Round your answer for the standard error to 2 decimal places. Okay, so I'm going to give myself a little bit of room here so we can make the calculation. Now remember, the standard error calculation is going to be S1 square divided by n plus S2 square divided by n. And these are n1 and n2, and that's the root of all value. So we're going to simply replace values of first set at 1.5 right here, 1.5. We're going to square that. We're going to divide it by the set of n, which was 45. We're going to add that to 1.1. We're going to square that, and we also had a set of 45. Take your calculator, take Desmos, take whatever it is you're utilizing. Make sure everything is under the square root. We're supposed to round to 2 decimal places. When I round mine, I get 0.28. We have a standard error in our calculation, which means movement from the center at 28 hundredths. I'm going to change my window just a little bit so I can see a little better here. It says the standard error for x bar 1 minus x bar 2 is the calculation that we just went through. A confidence interval is the general formula for which says to take the stat or the test statistic, again, your center point, multiply it times z star, and multiply that against the standard error. We'll add and subtract those values. We've done that in the past for populations, and we did it in the past for single means. It says for means, replacing sigma with the s causes us to use a t-distribution instead of that, meaning that we'll take the same test statistic, but we'll multiply it times t star, and we'll still use the standard error. By the way, I will show you how to find t star on your calculator, but on examinations, you'll be given the t star value for use. Make this just a little bit larger so we can see what's going on. So on a confidence interval level, if we're going to take the statistic and we're going to add and subtract t star minus or times the SE, it says if the population is approximately normal or the sample sizes are large enough, that has to be met. Sometimes you'll see the wording which says assume that all criteria has been met, and that just means that the sample sizes are large enough. Then we can approximate the confidence interval level for mu1 minus mu2. Remember, this is always about the population. It's not about the sample, because we already have the sample. We will take x bar 1 minus x bar 2. Again, remember, this, we can think about this. This is our statistic. The statistic is not one of them, but it is the subtraction of the two, which is the stat. The t star, I will show you how to do that, but you will be given that on exams. And then the standard error is here. If we put the two of these things together, t star multiplied by the standard error, that's the measurement of error. Remember, the measurement of error is equal to the entire value of the SE multiplied against t star or z star, depending on what we were utilizing in the past. The degrees of freedom for a t distribution is the smaller, always the smaller, of either set number 1 or set number 2, and it's always one smaller. We'll see that come into play when we do a problem. So we're going to use a t-distribution to answer this question. Assume the samples are random. I can't read behind my, or are random. Samples from a distribution that are reasonably normal distributed, and that the t-statistic will be used for an inference about the difference in the sample means. State the degrees of freedom used. And that's always important to do that. Find the endpoints of the t-distribution with a 5% beyond them in each tail. If the sample sizes are n1 is 9 and n2 is 11. Well, first thing we want to do is we want to look at our two sample sizes. We go to the smaller sample size of 9. That means that our degrees of freedom will be equal to 9 minus 1, or 8. So we have a degree of freedom for the first question in 8. Now we have to calculate the endpoints. Let me make a small drawing here for a second. If we're doing the endpoints for a t-distribution, and we want 5% in each tail, that means we want 0.05 here, we want 0.05 here, which automatically means that we have 0.9 sitting in the center. So we need to get the t star values for these endpoints. So I'm going to go to my calculator. I'm going to clear everything I have. I'm going to go to my distribution, or my second vars. I'm going to go down to, notice that we have two options here. Number 4 is inverse t, and number 6 is TCDF. T uses number 4 and uses number 6. We're doing inverse t for endpoints. We'll use number 4. We use the area always to the left, 0.05. Here's where it's important that we use the proper degrees of freedom, 8. We go down to paste, we hit the button, and we get a negative 1.86. We now know that our degrees of freedom gave us endpoints of plus and minus is already in the question for us, 1.86. So these points would be negative 1.86, positive 1.86, which would create 5% left, 5% right, or 90% middle. Use a t-distribution to answer the questions. All the same stuff. Find the proportion in a t-distribution above 2.1. So now we're looking for something different here. We're going above 2.1 and we're finding the proportion. The proportion means p-value. You're no longer looking for an endpoint. We have n1 at 12 size and n2 at 12 size. So therefore, right away, I already know that my degrees of freedom are 11, because either set 12 minus 1 would be 11. Now what I need to calculate is I need to calculate the area beyond 2.1. 2.1 is positive, and the area beyond 2 positive is going to 1E99. If it were negative, I would be going to the left, and I would be working from negative 1E99 up to 2.1 negative. So again, area, we're going back to our calculator. I bring up the calculator and I clear everything out. I go to second, distribution. This time I want the area, or number 6, for a TCDF. My lower number is 2.1, because remember we're working our way to the right. We're going with 1E99. Again, this is a super large number. It's a 1 times 99 tens. My degrees of freedom, we already stated those were 11, because both sets were 12, and that would give me a degree of freedom of 11, or either way. My area calculation is approximately 0.03 when rounded. 0.03 when rounded. That means that the area consumed beyond 2.1, or the p-value, is approximately 0.03. Very large question. A study has been conducted in 2006 where randomly selected U.S. adults age 18 and older were asked to give the number of people in the last 6 months to whom they discussed matters that are important to you. The average number of close confidence for the full sample was 2.2. So that's a number that was discussed in the average. In addition, the study asked participants whether or not they had a profile on social networking site. For 947 participants using a social networking site, the average number of close confidence was 2.5. 2.5. That's my first statistic drawn from 947 people with a standard deviation of 1.4. I'm going to go grab a different color here because I'm going to run into my second stuff now. And for the other 1,059, so here's my other N value at 1,059, who use a social networking site, the average was 1.9, so we have a different X bar with a standard deviation of 1.3. Circle all those values. We're going to need every one of them. Find a 95% confidence interval level for the difference in means between the two groups, U of S minus U of N, where U of S represents the number of close confidence using social networking sites, and U of N means the number of those not using social networking sites. Okay, very good. So when we go back and we look at that, we know that the formula we have to utilize is going to be X bar 1 minus X bar 2 plus or minus T star. And then T star is going to get multiplied by the standard deviation of the first square divided by the value of N in the first, added to the standard deviation of the second squared divided by the total number N in the second value. I'm going to give myself a place to work down here. So we're going to go fill in some groups from the values we have above. First of all, for group 1, or S, this is N of S. I know, first of all, that I had an N value of 947. I had an X bar of 2.5. And I had a standard deviation of 1.4. For my second set, or my N of knots, I had an N value of 1,059. I had an X bar of 1.9. And I had a standard deviation of 1.3. It's really just a matter of me plugging it into the formula. So again, we're going to work from the formula above. We're going to take X bar 1 minus X bar 2. X bar 1, 2.5, minus X bar 2, 1.9. We're then going to add and subtract T star. Well, the T star, I told you would always have it, but I will show you how to get T star for this value later. 1.646. Then we're going to multiply that by the standard error, and the standard error is going to be 1.4 square divided by N, which is 947. We're going to add that to 1.3, second standard deviation, squared, divided by 1059. Put all of that into your calculator, and you're going to put it in 2 separate times. When you put in the first one, you're going to get 0.50. And by the first one, I mean the one which is utilizing the minus sign. You always want to do the minus sign first. The second one you get will be 0.70. This is our CI value for 95%. So the intervals are one second. I got to change a battery. I'll be right back. I promise. Back at it. And new battery. So my 2 intervals are 0.5 when rounded, up to 0.7, again, when rounded. Testing for the difference of means. So now I'm looking for an actual t-test value here. Remember that we'll be looking at a population of mu1 equal mu2, because if we did a little bit of algebra here, that's mu1 minus mu2 equal to 0, which will be our null hypothesis. So we'll take our statistic, and our statistic will be derived from x bar 1 minus x bar 2. Anytime you have two means, you are going to subtract those two means for your stat. We'll subtract 0 because that's our null hypothesis, which I just showed on the left-hand side. And the standard error calculation we already know from calculating the confidence interval level is underneath of the square root formula there. It says if the population is approximately normal or if the sample size is large enough, then the p-value can be computed as the area in the tail or tails beyond t in a t distribution with degrees of freedom equal to the smaller n1 minus 1 or n2 minus 1. Best way to understand these is to do these. First of all, let's talk here. It says, in each case below, two sets of data are given for a two-tail difference in means. Test if each case, which version gives a smaller p-value relative to the others. Okay, so we want to look at the first one and the second one and figure out which one's a smaller p-value. Both options have the same standard deviation and the same sample sizes. Okay, well, let's think about how a t-test is derived. So when I'm calculating a t-number, remember, the further away a number is, here or here, the smaller the p-value will be generated from the center. So the more extreme or the larger number that I can create, a bigger test statistic, this will create for us a smaller p-value. Larger test statistic will create a smaller p-value. So when I look at the formula says that I should take x bar 1 minus x bar 2. I should subtract 0. And I should divide that by the square root of s1 square over n1 plus s2 square over n2. Well, remember what makes a fraction large? Either making the top really large or making the bottom really small. So if I go into this first option where it says I have x1 at 23 and x2 at 18, well, I want you to focus on this option right here, option 2. I want to look at that and go, you know what? So if I look at 23 and I look at 18 in the numerator, if I look at 23 and I look at 12, remember, I'm subtracting these things. 23 and 18 are going to produce 5. 23 and 12 are going to produce a larger numerator. So my numerator value is going to increase itself. 12, 8, 9, 10, 11. I have 11. Larger numerator, smaller denominator, makes for a bigger test statistic. Option 2 is going to create a larger fraction. You kind of got to go into it the mindset of just simply sitting the numbers in there and seeing what happens. Why don't I pay attention to the bottom? Because remember they said that the standard deviation and the sample sizes were the same. So the denominators would be equal. But the 11 would create a larger numerator. Let's look at that in option number 2. Now in option number 2, now the means, they have the same mean value. So the mean, the numerator is not going to change. The only thing that's going to change now is the denominator. So now we got to look at the denominator and go, okay, which one is going to produce a smaller value? Remember, the denominator needs to be smaller, it'll make the number bigger, or the numerator needs to be bigger to make the number bigger. So I look at these two ones and I'm trying to figure out, okay, who is going to give me a smaller value? Well, if I look at set number 1, I have an S1 of 16 and I have an S2 of 15. And on option number 2, I have an S1 of 4 and I have an S2 of 5. So now my set numbers are, if you take a 16 and you square it, if you take a 15 and you square it, that's a large number. If you take a 4 and you square it, and you take a 5 and you square it, that's a much smaller number. Why am I focusing on the smaller one? Because now I have a situation in which I have a big number in the numerator, which stayed the same. So I'm going to write same because the x1 minus x2 remained the same, but now I have a smaller value in my denominator. Kind of like this, 5 over 4 compared to 5 over 1. 5 over 1 is much larger than 5 over 4. If you can make the denominator smaller, then you make the number bigger. Option number 2 does that for me. The last one, both have the same x bar and x bar 1 and x bar 2. So again, we have the same notation in the numerator. The difference here is, though, that the end values are changing. Now, what happens into a fraction in a fraction? Well, first of all, what happens in a fraction value? If I have a fraction value with a large denominator, again, a large denominator, that's going to make that number smaller. So as my large denominator makes my fraction smaller and smaller, I'm, in essence, going to make the entire number larger. What do you mean, Eating? You just said larger, you just said smaller. For instance, let's say that I have 1 over 2 over 3. 2/3 is pretty close to 1, and 1 divided by 1 is pretty close to 1. But if I compare that to 1 over 2 over 279, 2 over 279 is very, very small. And if I divide 1 by something very, very small, that number gets bigger and bigger and bigger and bigger. In essence, as I make the denominator of the complex fraction bigger, then it will yield a number which has a smaller denominator. And if I can make a smaller denominator, I create a larger number. Therefore, again, option number 2 will create a situation in which I have a same numerator, but I have created a much smaller denominator. So you can see the goal here is to create a smaller denominator when the numerators are the same, or if the denominators remain the same as in the first, we want to drive the numerator to be larger. This takes a little bit of going over and working with, but you have to be conscious of how a fraction physically works. Use the t-distribution and the given results to complete the test of the given hypothesis. So we're going to go through the whole hypothesis here. Assume the results come from random samples, and if the sample sizes are small, assume the underlying distributions are relatively normal. So we get to assume all conditions have been met, is what we say. So in this first one, it says test H of O where mu1 equal mu2, so we know that we're centered at 0. Our H sub A, or our alternative, is two-tail, because we have not equal, so we know we have a two-tail test, and that's important. We have sample of x bar 1 equals 15.3 with a standard deviation of 11.6. We have a sample of 100. X bar 2 is 18.4 with a standard deviation of 14.3 and a set of 80. Round your answer for the test statistic to 2 decimal places and your answer for the p-value to 3 decimal places. Please be careful when we're doing that. So let's do our first value to find t. So our t-score will come from x bar 1, 15.3, minus x bar 2, which is 18.4. Those two values will be subtracted, and then we'll take away the null hypothesis, 0. We'll divide that by the square root of 11.6, and we'll square that. We'll divide it by 100. We'll add to that the second standard deviation of 14.3, again, square, but this time we'll divide it by 80 for the set of n. Our approximation is negative 1.57. Again, be careful putting that into your calculator when you're doing your rounding. So our test statistic is 1.57 negative. Now this is where students get a little hung up sometimes, but we're going to try not to be hung up at all. Remember what we just found is that on a distribution, here is our 0. We are at negative 1.57. We're testing from negative 1.57 or more extreme than 1.57. So we're going to go to our calculator and we're going to get a TCDF, or an area calculation. So I go and I go to my second and my vars. I want to find area of a t-value, number 6 TCDF. Remember, I'm working my way from the negative 1 second E99. Very, very, very far to the left. Here, I need my negative, and here it's a negative 1.57. My degrees of freedom. Remember that my degrees of freedom in this calculation are 1 smaller than the smallest set, 79, because my smallest was 80, and my degrees of freedom, therefore, is 79. When I do that calculation, I get about 0.06. However, remember, going back, this is a two-tail design. And on a two-tail design, we have two sides, which means our calculation for area becomes double. Just hit times 2 in your calculator. And we are at approximately 120 at 3 decimal places. Again, we have to double the p-value because we have a two-tail test. So our p-value is 0.120. What is our conclusion on a 10% level? Well, remember, the whole basis of a conclusion is how does the p-value compare to the alpha level? The alpha level for us is 10%. Our p-value is 120, or 12%. Our p-value is greater. So what do we do when our p-value is greater? We do not reject. Next question. Next question talks about drinking tea. Now, I'm going to have you run through this, but I am going to help you set this one up because I think it would be awesome for you to utilize it. So I'll get you to the place where you've almost got answers, and then you're on your own. So it says drinking tea appears to offer a strong boost in the immune system. We've had this discussion before. In the study, we see that the production of interferon gamma, a molecule that fights bacteria, virus, and tumors, appears to be enhanced in tea drinking. In the study, 11 healthy, non-tea drinking individuals were asked to drink 5 or 6 cups of tea a day, while 10 healthy non-random non-coffee drinkers were asked to drink the same amount of coffee, which has caffeine but not the L-theanine. The groups were randomly assigned. After 2 weeks, blood samples were exposed to the antigen, and production of interferon gamma was measured. The results are shown in Table 1 and are available in the Immune Tea. Anytime they tell you that right there, there's a data set inside of StatKey that contains this data. The questions of interest is whether the data provides evidence that the production is enhanced or is different in tea drinkers. Use subscript 1 for the tea drinkers. So we'll use subscript 1 for the tea drinkers and subset 2 for the coffee drinkers. So a couple of questions. First of all, the study is, well, oops, very sorry about that. Undo that right there. Change. The study is, well, if we take a look at this particular study, it's definitely an experiment. State the hypotheses. Well, this hypothesis, remember, always talks about the population. We want to know if the subset 1 or the tea drinkers are the same as subset 2, the coffee drinkers. What's the alternative to that? Well, the alternative to that is that the first set produces more interferon gammons than the second set. Do the tea drinkers have an elevated level? That was, and it was said right here, I'm underlining it, enhanced in tea drinkers. So we want to know if tea drinkers are more. The test statistic. Okay, well, for the test statistic, you're going to have to know a couple of things. First of all, in the test statistic, you're going to have X bar 1 minus X bar 2, which you do not have at this particular time. You're also going to have to know the standard deviation of the first set, and you're going to have to know the standard deviation of the second set. Again, which at this particular time you do not know. I'm going to help you get that data, and then I'm going to let you go and complete the rest of the data. So how can we get this data? Well, and in my next slide, it'll be part of it, but I'm going to walk you through it. So what we're going to do is we're going to go to StatKey itself. So we're going to StatKey. And in StatKey, the first thing I'm going to do is go grab the data file set. So I'm going to click on Statistics. I'm going to go to the data set. In the data set, I'm going to scroll down through the data set, and I'm going to look for the appropriate data file. Now remember, the data file was right here, immune T. I go back to here, and I go down and I start looking for immune T. H-I, right here. Click the CSV, and it'll download to your bar. You do not need to open it, just leave it in your bar. Go back to StatKey. Go to one quantitative and one categorical right here. And we're using descriptive statistics. Click on descriptive statistics. Upload the file, choose immune T. You will have to tell it, first of all, quantitative. Which data set is quantitative? Well, that's the number set. Which one's categorical? It's the T. Tell it to open. Your data you're looking for is over here on the left side. The mean for the tea drinkers is 34.818. The mean for the coffee drinkers is 17.700. The standard deviation is listed below the tea, and the standard deviation is below the coffee. You'll use this data in order to populate this formula. Once you find this test statistic, then you'll want to put that test statistic, and I'll give you a hint, it should be positive. You're going to test for the area greater than that test statistic. Since this test statistic is going to be positive, on a right tail test, you're going to calculate the area as extreme or more extreme than that value. So these are hints that you're going to be out here somewhere in a positive region. You're going to test everything over here. So you're going to test this p-value. But I want you to look back up. I want you to pay attention to the two-tailed test because it's a not equal here value. And because we're looking at a greater than, this is a one-tail test. Do not double your p-value like we did in the last one. It will simply be the area greater than. And then make the decision on what you think the conclusion will be. Make sure you round your p-value to 3 decimal places. Hope you have a good time with that. Email me if you have a question with it. It's been a pleasure. Thank you very much, and congratulations. That's the last chapter we'll be working on in this particular book.